with 6 different positions available for substitution on the octahedron, there are numerous ways of substituting it. So let's look at a couple of the other really important, common, and interesting ones. So in this case, we're going to look at pairs of substitution. So again, we're going to start with sulfur hexafluoride. But in this case, we want to add both bromine and chlorine substituents. And I'm being kind of careful in how I've arranged them on the molecule so that the like atoms are across from each other. So here we have a SBr₂Cl₂F₂. So we have lots of stuff going on here, and we want to ascertain the point group symmetry of this particular molecule. And this is another case where drawing it as a 6-pointed star can actually be rather useful. So depending how we judiciously choose our faces in this case. So let me make this be the front face here. Okay. So with this particular set of assignments, I have fluorine at the top. At the lower right, I'm going to have a chlorine atom. And at the lower left, I'm going to have bromine. So that gives us the front or near face. And I notice that going back goes from chlorine to bromine. That's this particular position here. So I have a bromine. I have a chlorine at the back left. And then the last but not least position is going to be a fluorine. And I notice in my 6-pointed star representation, I notice that the atoms that are across from each other, that are all trans, are actually across from each other in the 6-pointed star representation. So this preserves an important feature of our molecule and how it's substituted. So one of the nice things about this type of representation, it makes it a little clearer what's going on if we look for particularly C2 rotational axes. So, for example, suppose I look for an axis along here. So, if I do a rotation along the particular chlorines, it's going to take chlorine, sulfur, and chlorine are along the axis, so they're not going to change. And it's going to take, I'll show this here. It's going to take this bromine, it's going to flip over to the other side. It's going to flip across. The fluorine at the bottom is going to flip to the top. So that's going to swap those particular substituents. Similarly, if so let me just draw where that line was. So over here, it would be through here. So this is going to be a C2. Now part of this is the defects of my ability as an artist, but it's somewhat clearer if you draw it really well that across this line, if you flip it over, this bromine would go to this bromine, and then fluorine would go to that fluorine. So it really does confirm it. Sometimes it's easier to see with this representation, sometimes it's easier to see with that one. But we have a number of these C2s. We also have a C2 that goes through the bromines. So we also have a C2 that goes in this direction, which over here would be along there. So I notice that I have 2 C2s, and one thing I notice about the C2s is that they are perpendicular to each other. That might be a hint. And then last but not least, I look for a C2 that goes through the fluorines. So I actually have a C2, which will take chlorine to chlorine, bromine to bromine, and this will stay here. So we have a C2 along there, which would be this particular axis in the 6-pointed star representation. So my high order rotation axis is going to be a C2, and I have 2 other C2s that are perpendicular to it, which tells me that I must have a D group of some type. I have a D2. So let's just notice that we have D2 so far. Let's see anything as far as mirrors. Well, in the representation on the left side, I do notice that if I think of a plane a mirror plane in the plane of the meridian, so essentially going across the waist of the molecule, that it will reflect fluorine at the bottom to fluorine at the top, which tells me that I really do have a horizontal mirror. It's perpendicular to the C2 high order rotation axis that's going vertically, so I have the point group D2H. So this is an example of D2H in octahedral molecules. And now for our next compound, let's try this particular molecule. We notice in this particular case that we have substituents that are cis to each other and others that are trans. So long as we have monoatomic monodentate ligands and we have at least one set that is disubstituted and is trans, we're guaranteed to have at least one non-trivial symmetry operation, the mirror plane. So let's see if we have any other important symmetry operations for this particular molecule. We might try to look for a C2 axis, for example, along the x-axis, because this would take bromine into bromine and chlorine into chlorine, but it would take fluorine into iodine, which are not the same, so we don't have a C2 operation here. If I try to look for high-order rotation axes perpendicular to the equatorial plane here, that would take chlorine into iodine, for example, and that doesn't work. If I try to look for a C2 axis along here, it would take chlorine into fluorine, so that also doesn't work. The only non-identity symmetry operation that we have here is going to be a mirror plane. We notice that we do have a mirror plane in the equatorial plane, roughly the plane of the board here, and that reflects, kind of show where that's going to be. This is going to reflect the bromine at the bottom to the bromine at the top, and then iodine, fluorine, and the two chlorine atoms, since they are already in the mirror plane, they're not affected by it. So they essentially have the top of the atom mirrored into the bottom half, so that works. So the only symmetry operation that we have here, other than we have the identity and we have a mirror plane, and because those are the only two symmetry operations that we have, that tells us that we have the point group CS. See if we can come up with any other substitutions that will lead to a different point group symmetry. So here's another example. So here we've added water, which is a very common ligand for transition metal complexes, at one of the positions. So now we want to see what particular symmetry operations this particular molecule is going to have. So we do the same things that we normally would do, is we look in the sort of z-axis to see if we have our C4 or some remnant of it, but that would take bromine into iodine or bromine into fluorine, so we have no non-trivial rotational axis in the xy plane. We also can look for a C2 along the x-axis. That doesn't work. We look for a C2 axis along the y-axis. That also doesn't work. So we see that we no longer have any Cn axes where n is greater than 1. We just have the identity. So let's look for the mirror plane. So see, we have a mirror plane. Well, if I look for a mirror plane here, that would take chlorine into bromine, doesn't work. If I try along here, it would take bromine into iodine, which doesn't work. And then let's even try in the plane of the board, and we see that that would take iodine into water. And since iodine and water are obviously different, we have no mirror planes. And if we look carefully, we notice that we don't have inversion, we don't have any improper rotations. So what we're left with is only the point group C1, because the only symmetry operation that is left is the identity. Not only do transition metal complexes, particularly the octahedral ones, feature monodentate ligands, they can also have bi, tri, or multidentate ligands. As far as the bidentate ligands, two are of particular importance. We know, for example, that ammonia has a lone pair on nitrogen, and that would make a monodentate ligand. But if we link two amino groups together at the ends of an ethyl chain, we end up with a bidentate ligand called ethylenediamine, and we tend to abbreviate this as EN. Another combination has an amino group on one end and a carboxylic acid group on the other. And this we recognize as the conjugate base of glycine, so this is called glycinate. So the lone pairs here are nitrogen or on one of the oxygens from the carboxylate. So these are two of our bidentate ligands. And once we start to add bidentate ligands to our octahedral complex, we end up with some interesting results and some new point group families. So let's look at a couple of examples where this occurs. Previously, we had used sulfur as our center of our proposed complex, a main group element, but we can also have a transition metal at the center. A very, very common one is going to be cobalt 3+. Cobalt 3+ is makes extremely stable complexes. And again, we can highlight the trigonal symmetry of our transition metal complex. I'll highlight that here in green, sort of our front face of our thing. So now, let's look at what happens if we have three ethylenediamine ligands that are bound to our transition metal. And we're going to use a shorthand for ethylenediamine. We're going to simply represent the ethylenediamine as a nitrogen atom where it binds to the metal, and then we're going to denote the rest of the molecule simply by a curve. So this is the shorthand for the ethylene chain between the two diamines. Now if we can draw this as, you draw the front face as in green just to highlight the structure here. So again, we're using our 6-pointed star representation, which is particularly effective when we're looking at bidentate ligands. And represent our red dot there. And then we can connect the ends of the chain. Now we notice something that's interesting about this particular set is that for this isomer of the cobalt triethylenediamine ion, so we often represent this ion this way, we notice it has a 3+ charge, that in the arrangement we've drawn on the whiteboard, that the front ring is in green, the back ring three-member ring is in black, the two rings are parallel to each other, and they will be in an octahedron. And we notice that going from the front triangle to the back, we make a turn to the right. So we notice that nitrogen here is in front, the nitrogen there is in the back, and that going from the front to the back, following along the chain, we make a curve to the right. It's a clockwise twist. And that's going to be true for all three of the ligands. Because that is true, and the Latin word for right is dextro, we refer to this as the capital delta isomer. The reason for this notation is that delta is the Greek letter D. So this is a capital D in Greek to correspond to the Latin D that goes for the word dextro, which means right. So this is one of the isomers, one of the possible ways of arranging the three ethylenediamine ligands on around the cobalt 3 plus transition metal at the center. There is a second way that we can arrange our ethylenediamine ligands in this particular complex. Let's draw our basic structure one more time. Emphasize the central triangle there in front. So again, we're representing the ethylene chain by a swirl. And just emphasizing the nitrogens at the end because they have the lone pair. So we can also draw this in terms of our six-pointed star representation. So let's do that. Okay, and we put our nitrogens again. Notice something different about the other arrangement that we can do. We can actually come up with a second distinct representation. So this is the second isomer, and we notice that in this particular case, that going from the front to the back, remember the green triangle is in front, the black triangle is behind the plane of the board, the two triangles are parallel to each other. They're going from nitrogen here to nitrogen in the back. Following along the chain, I have to go to the left. I go counterclockwise. Because we have to go to the left, and the Latin term for left is levo, L, we use a capital L in Greek, lambda, to represent this isomer. So this is the lambda cobalt triethylenediamine 3 plus ion. And what's interesting about this, beyond the fact that we have two isomers, is the fact that each isomer is optically active. So the delta and the lambda isomers are mirror images of each other, which are not superimposable. So that tells us that each possesses the property of optical activity. One will rotate plane polarized light to the right, and the other will rotate plane polarized light to the left, and by equal amounts. And it's an interesting experiment that we do in the inorganic chemistry lab, is we synthesize this particular complex, and in the initial synthesis we get a racemic mixture. We get a 50-50 mixture of the delta and the lambda isomers, and then we're able to separate them. We're able to resolve one particular chiral component by adding in a derivative of tartaric acid, essentially another chiral resolving agent, and we're able to precipitate out one specific isomer. And then we're able at the end to confirm that we've actually synthesized and isolated the correct isomer by doing polarimetry on it, and we can actually measure through polarimetry the optical activity of that isomer. So the important thing from the point of view of group symmetry is, so what is the symmetry of these things? Well, we can easily recognize, looking down this particular axis, that we have C3. We have a C3, so it will rotate. This nitrogen goes to that nitrogen, this nitrogen goes to this nitrogen. And the same works for the nitrogens behind, and the C3 rotation brings along the ethylene chain. So we do have a C3. So let me erase this to the side, and we'll note that we do have a C3. So our high order rotation axis is going to be a C3 in this case. Do we have anything else? Well, we want to look for C2 axes that are perpendicular to the high order rotation axis. So one place to find one of these is to go right along here. And if I look along this particular axis, what happens if I do a C2? Well, it's going to flip this nitrogen here, which is in front of the board, to the nitrogen that's behind it. The nitrogen behind it is going to get flipped to the front, and then the parts of the ethylene chain which are in front will go behind. So it's going to flip the ethylene chain as well. We see the same thing here. We have a nitrogen in front, it's going to get flipped behind. So along this particular axis, we have a C2. And we notice that this C2 axis is perpendicular to the high order rotation axis. Okay. And then we can continue along this axis, for example. We can perform a C2 rotation, and it will take one part of the molecule into the other. And then last but not least, if we go this way, we have a third C2. So we notice that we have, among other things, we have 3 C2s which are perpendicular to our C3. So what does this tell us? It tells us that we have the point group D3, at least. So now we want to see, it's got to be some version of the D3 family of point groups. So we want to look to see where do we have mirrors. Well, we can see pretty clearly in this drawing that we have no horizontal mirror. A horizontal mirror would have to be a mirror in the plane of the board, and we can't have that because we have a ring pointing up in the front, but there's no corresponding ring behind the plane of the board. So we can see right away that we don't have a horizontal mirror. What about vertical mirrors? Well, you might try for a vertical mirror like this, which would have worked if we only had monodentate ligands, but we notice that on this side I have an ethylene chain going to the left, but there is no corresponding ethylene chain going to the right. Because of that, that means that I have no vertical mirrors either, and there's no dihedral mirrors. So we have no mirrors at all. So as a result, we have our first example of the point group D3, just D3 by itself, not D3D, not D3H, just D3. And the way that we often see the arrival of this point group is once we start to add bidentate ligands to our molecule. Continuing with the idea of bidentate ligands, let's look at one more example of a transition metal complex with bidentate ligands and see how that affects the point group symmetry. So we're highlighting our front triangle in green here. So we'll be able to put this over here later on. And in this case, we're going to replace the ethylenediamine ligands with glycinate ligands. And we're going to connect the ends with a line, but also just to emphasize the fact that the two ends are not unique, one's nitrogen and one's oxygen, we're actually going to turn this into an arrow. Just essentially borrowing a notation that's very common in biochemistry to denote protein strands. But in this case, we're just using it to show the directionality of the chain going from the amino end to the carboxyl end. So now we can put the here. In fact, let me do one minor color coding here also, which will emphasize the nature of the molecule. And We usually color code oxygen as being red, so let me do that. And then last but not least, we're going to draw the chain connecting the molecule. So this is our molecule now. So we have 3 glycinate ligands attached to our cobalt 3+. So we actually have a neutral molecule here. And we want to assess the point group symmetry of this molecule. And we figure that we're going to proceed in a similar manner to how we did for the tri-ethylenediamine complex. So again, we want to look along this axis. And we notice that if I rotate by a C3, it's going to take nitrogen to nitrogen, nitrogen, nitrogen in the front. So the front triangle consists of nitrogen, takes one to the other, that's fine. For the back triangle, each of those is an oxygen, so as we rotate, it's going to take this oxygen to that one, and so on. So we do have a C3. So we know that we do have a C3 high order rotation axis. So next we want to look for C2s that are going to be perpendicular to the high order rotation axis. So we might try, as we had before with the ethylenediamine complex, and look for a C2, for example, along the x-axis here. So that would take an atom here in the front to one in the back. And this worked when we had ethylenediamine because both of the ends of ethylenediamine were nitrogens. But here that's not true. One is nitrogen and one is oxygen. So we no longer have a C2 along this axis. Along this axis, we no longer have a C2. And along this axis, we no longer have a C2. And this is because of the directionality and the different ends that we have. So since we no longer have any C2s that are perpendicular to our high order rotation axis, what does it tell us? It tells us that we don't have a D group. We have a C3 group of some type. Okay. So then we want to look for mirror planes. Well, we want to look for a mirror plane in the plane of the board, and we know that's not going to be there right away because of the way we've drawn our three-pointed star. There's no triangle behind the green triangle, which would have to be there if we had a mirror plane in the plane of the board. So there's no horizontal mirror. If we look along here, again, we try to look for a vertical mirror. This vertical mirror would have to take this arrow and mirror it, and there have to be another arrow on this side, and there isn't. So that tells us that we don't have any vertical mirrors either. Since we have no vertical mirrors and no horizontal mirrors, all we're left with is a point group assignment of the group C3. So C3 is a perfectly good group. We don't see many examples of it, but a typical example of where this might arise is in octahedral complexes where we have 3 bidentate ligands, but that the ends of the bidentate ligand are different. So I thank you for your attention. Don't forget to subscribe. Have a good one.